Electrolysis is sort of the opposite of what we've been talking about so far. In an electrolytic cell, as opposed to a voltaic cell, here we don't have a spontaneous reaction that is producing current. We're using current, electrical current, to cause a non-spontaneous reaction to happen. And so that's called electrolysis. Has nothing to do with the removal of hair, right? This is chemistry word here. So if we put hydrogen and oxygen together under the correct circumstances, they will form water, and that's a spontaneous reaction. And we can, if we have it set up right, we can use that reaction in the fuel cell to produce electrical current. But if we supply electrical current, if we put electrical current in, we can cause the reverse reaction to occur. We can take water and decompose it into oxygen and hydrogen. So one of the ideas here is that if you had a solar-powered electrolytic cell, you could use that to generate hydrogen to be used in the fuel cell. The problem we always have, though, is that heat tax, right? Every time energy goes through a transformation, you lose some of it to heat. And so not only can you not get ahead, you can't even break even. That's how they talk about it. So this is an illustration of the electrolysis of water. We've got an anode and a cathode, and here we've hooked the battery up to cause the electrons to go in the opposite direction. So we're going to form oxygen bubbles over here and hydrogen bubbles over there, and if you attach balloons, you would see that you're getting twice as much hydrogen as you get oxygen. Right? Some of you remember when I put the 9-volt battery in water, and we saw the little bubbles forming? That's what was happening, right? The battery is causing the water to decompose into hydrogen and oxygen gases. So, breaking water apart, unless you're trying to make hydrogen for a fuel cell, is not very useful. There's a lot of other uses of electrolysis. We can take naturally occurring metal oxides and reduce them to produce the pure metal. So how do you make sodium metal? Sodium's really reactive. It reacts with the moisture in the air, right? So you're not going to, just be digging in the dirt and find, a chunk of sodium. Not going to happen. Any sodium that's out there is reacted with something else, and it's part of a compound. But through electrolysis, you can take something like sodium chloride, and you can reduce the sodium ions into sodium atoms and get the pure metal that way. We can also plate metals onto other metals. So silver plating. People used to have silverware, right? Silverware, utensils, forks, spoons, and knives, they were made of silver, right? And they were kind of expensive. But people, really shiny and beautiful and everything. And then people figured out that you could just put a thin coating of silver on the outside of a cheaper metal, and it would look like silver, right? So you can plate a less expensive metal with the more expensive. So this is an illustration of an electrolytic cell for silver plating. So here you have your object to be plated, and so you're pumping electrons into here, and the silver ions that come around are going to gain an electron and form a silver atom. Well, silver atoms aren't soluble in water. So right where they got the electron, they're going to stay, right? And so they're going to deposit on here. So we have this silver electrode here. taking electrons out of that, causing these silver atoms to become silver ions. They go over here, and they get the electron back, and now they're silver again. So we're just moving silver atoms, essentially. But you can do that with lots of different metals. A more generic term is electroplating. The voltage that you need for electrolysis, of course, is going to depend on what the specific half reactions are. Here we have a voltaic cell where we have zinc being oxidized and copper ions being reduced. This is an electrolytic cell involving the same substances, but we're pushing electricity into it, and so we've got copper being oxidized and zinc ions being reduced. So in an electrolytic cell, the anode and cathode are going to switch because you're forcing the current to go in the opposite direction. So I think it's best to learn what's happening at the anode and the cathode in a voltaic cell. And then if you have to identify something in an electrolytic cell, just switch everything. Right? So here, this was the anode. It was negative. Over here, this is going to be the cathode. This was the cathode. Now this is the anode. Not confusing at all. So what's common to all electrochemical cells is oxidation happens at the anode, reduction occurs at the cathode. So, red cat. In a voltaic cell, the anode is the source of the electrons, so the anode is going to be negative, which makes sense to me because anions are negative. The cathode draws the electrons. The cathode is positive because cats are positive, right? In the electrolytic cell, things are going backwards. The electrons are drawn away from the anode, so the anode is positive, and the electrons are being forced into the cathode, and so the cathode is negative. So remember this part, and this is opposite. Okay, which statement is true for both electrolytic and voltaic cells? The cell spontaneously produces a positive voltage. Electrons flow from anode to cathode. Oxidation occurs at the cathode. I hear little mumblings, but I can't understand anybody. So you're all saying C, which is correct. Oxidation occurs at the cathode. The electrons are going to flow in the opposite direction. Voltaic, they come from the anode to the cathode. Electrolytic, they go the other way, from the cathode to the anode. And only voltaic cells will spontaneously produce a positive voltage. An electrolytic cell requires you to put a voltage into it to make anything happen. Any questions? Did I do that wrong?
Yeah. Yeah, because red cat.
I changed my notes. I was like, I wrote that wrong.
I fooled myself. What? Okay. That was bad. So, what I was remembering is that this stays the same. What I did not notice is that this is wrong. This is wrong for both, right? Because red cat. Hence all the puzzled looks. Thank you. Yeah. Yeah, you were sure and you were wrong. Exactly. So, my bad. The good news is I think questions like that are kind of stupid, and I'm not going to ask you that on an exam.
Yeah,
If you apply a voltage to, a system, you don't always get what you think you're going to get, right? So this is about predicting electrolysis products, what's actually going to happen. So first we're going to talk about pure molten salts. So you could take sodium chloride and you can heat it up really, really, really hot, and you can turn it into a liquid. It's called molten sodium chloride. In that molten liquid state, the sodium ions and the chloride ions can move. It will conduct electricity. And so you can do electrolysis on that, and you can but you can reduce sodium into sodium metal. Nothing else could really happen. Cl minus can't be reduced any further, so that one's going to get oxidized. Sodium ion can't be oxidized more, so that one's going to be reduced. There's not much question about what's going to happen. If our molten salt has more than one cation or more than one anion, then we have to think about which of the cations is more easily reduced. And this is an important note. Those standard potentials in the table are not correct for molten salts. So you can't use the number, but the relative order is correct. So you can still look at that table and see, well, which one of these would be reduced first, more easily. So if you had sodium chloride and potassium chloride melted together, you got two possibilities here. The sodium could be reduced or the potassium could be reduced. We look at those standard potentials, and the numbers aren't correct, but this number is smaller. It's closer to 0, and so that tells us that the sodium is going to be reduced before the potassium. If there's more than one anion, then you also have to figure out which anion is going to react. It's going to be an oxidation. Sodium bromide, sodium chloride, we have two different anions. Bromide could be oxidized to bromine, chloride could be oxidized to chlorine. And so here we're going to look at these potentials. And so I find the book's way of doing this to be it's ludicrous, if you ask me. So this is the way I think about it. I'm going to reverse the equations so that they reflect what I want to happen or what is going to happen, right? So this is an oxidation half reaction, right? Because this is losing electrons. If you look this up in the table, though, it only shows you reduction half reactions and reduction potentials. So here I'm going to flip these, so I'm looking at oxidation, and then what I do for this is I change the sign, right? And then I can look at the one that's more positive is going to happen. One is closer to 0. So the book always gives you reduction potentials, and so then you have to think, well, for the one I look at which is higher, and the other one I look at which is lower. Any questions? Yeah.
So if you were to flip the sign of both of those, what is the higher reaction do you want both these symbols?
Well, I already flipped the sign.
Oh, okay.
Yeah.
Okay.
Yeah. So if you look at these, they're going to be positive in the table. Yeah. So that's why I put that in there, because otherwise it looks like it's wrong. Okay, so that was talking about molten salts. If we're doing electrolysis in an aqueous solution, which is much easier, you can do that at room temperature, not at crazy high temperatures, things get complicated because the water itself can be electrolyzed. So, like with the battery, we can have the oxygen, oxygen forming and hydrogen forming. So these are their standard potentials, but in pure water at room temperature, the hydrogen ion and the hydroxide ion are not at standard concentrations, which would be 1 molar. You don't have 1 molar H plus and 1 molar OH minus. So those are their standard potentials, but in water, at the actual concentrations, these are going to be the potentials. And so the potential for the cell is negative 1.23 volts. Of course, pure water does not conduct electricity, but if you put something, an electrolyte in there, then you can electrolyze the water. So you think about the 9-volt battery in the glass of water. Tap water is not pure water. It still doesn't conduct very well, so put a little salt in there with the battery. The battery is a 9-volt battery. It has plenty of voltage to electrolyze the water. So if we have a sodium iodide solution, we have two possibilities for the oxidation. We could have water being oxidized to produce oxygen, and iodide being oxidized to produce iodine. So we have to look at those potentials. This is the potential for the oxidation of water in actual water, not at standard conditions, negative 0.82. And the standard potential for the iodide is negative 0.54. For reduction, we could reduce the water, that'd be negative 0.41, or we could reduce the sodium. That's going to be negative 2.71. So at each electrode, the reaction that has the less negative E is going to be the one that happens. So for this one, if we're applying voltage, we're going to hit this one first. This one's going to happen, and that one's not going to happen, because this is going to happen easier, right? Between these two, the water is going to be reduced rather than the sodium. So you can't get sodium from sodium chloride in an aqueous solution because the water will get reduced before the sodium is. So this is just a picture of that with the correct half reactions chosen. So the iodide is being oxidized and the water is being reduced. And if that wasn't complicated enough, we have an additional complication called overvoltage. So some non-spontaneous reactions need a little extra push. Not just the voltage that we calculate, but you actually have to give them more, an overvoltage. So for water, this, we said was negative 0.82 volts. But due to kinetic factors beyond the scope of this discussion, the actual voltage is 1.4 volts. So we don't need to understand exactly how that's happening or what's happening. You just have to know that sometimes you need more voltage than you calculate in order to get that going. There's good reasons, and we don't want to go there. Okay? So we can look at stoichiometry. We can look at stoichiometry in electrolysis reactions. So the electrons are acting as a reactant. So we have copper ions, and each copper ion needs 2 electrons to make a copper atom, right? So we have a stoichiometric relationship here. 2 moles of electrons for every mole of copper. The quantity of electrons is not measured with mass because they're really, really tiny. We measure electron quantity with charge. So the number of moles of electrons is determined from the total charge that goes through that cell. And of course, that's going to depend on the magnitude of the charge of the current and on the time. But we've got the Faraday constant, this many coulombs per mole of electrons, and we can look at the current flowing, which is coulombs per second. So we take the current, coulombs per second, and we multiply by the time in seconds, and we get the charge in coulombs. And then we can use Faraday's constant to convert coulombs into moles of electrons. Clear as mud. So silver plating uses the reaction Ag plus E minus to form Ag. How many moles of electrons must pass through an electrolytic cell for silver plating in order to plate 3 moles of silver? So if we want to make 3 moles of silver, how many moles of electrons do we need? 3, right? It is just that simple. So here's a little more advanced example. We can plate silver out of the solution using this half reaction, and this is saying how much time in minutes would it take to plate 12 grams of silver using a current of 3 amps? Now this might be a good test question, something like this. Well, 3 amps, an amp is coulombs per second. So that's 3 coulombs per second. And we've got 12 grams of silver. And so I tend to approach things using dimensional analysis like whenever possible. So what I'm given here is 12 grams of silver and this current, and then they're asking me to find the time in minutes. So I'm trying to convert 12 grams of silver into minutes. And obviously we're going to have seconds before minutes. So how do we convert a mass of metal into time? Well, there's a relationship hiding in our chemical equation here, right? There's 1 mole of electrons per 1 mole of silver, right? And then, blanking on the Faraday constant. $93,563 is something like that. Anybody have it? 96,489? 85. I got the 5 right. Coulombs per mole of electrons. So that's something that's not going to be given in the problem, but it'll be given in the useful information part if this was an exam question. So this is going to allow me to convert moles of electrons to moles of silver. Can I convert moles of silver to grams of silver? Sure. That's a common thing we did in Chem 1A. So grams of silver to moles of silver. And then I can use this to convert that to moles of electrons. And then this I can convert from moles of electrons to coulombs. And I can convert coulombs to seconds using the current. Finding that path for the dimensional analysis is the hardest part of a problem like this. Once you find the path, you can just follow a pattern, which if you were with me for 1A, each of these arrows is going to represent a conversion factor. So I have 1, 2, 3, 4 arrows. I'm going to have 4 conversion factors. So I'm going to start with my 12 grams of silver, and I'm going to have 4 fractions. Come on, move over. 25.2 degrees Celsius. These are the units that are going to be on the top of those conversion factors. So grams of silver to moles of silver. So this is moles of silver. And then I'm going to moles of electrons. So this next one is moles of electrons. And the next one is coulombs. What did I do? I can't count. How many arrows are there? 5. You guys gotta help me out here. I'm sick. Literally. Coulombs to seconds to minutes. Pretty sure I'm not contagious though, so. So grams to moles to coulombs to seconds to minutes. Same thing right across the top here. Grams of silver I'm trying to get rid of. That's going to become the denominator in the conversion factor. So grams of silver cancel out. This is a relationship I already know. That's the molar mass of silver. Find that on the periodic table, 107.9. Is the mass of 1 mole of silver. Then moles of silver comes down here. There's 1 mole of electrons to 1 mole of silver. We got that from the chemical equation up here. And we're going to put moles of electrons down here. That's the Faraday constant, 96,485 per mole. Here, I'm going to have coulombs come in the denominator, and that comes from my current, 3 coulombs per second. And then seconds down here, and this comes from general knowledge. There are 60 seconds in 1 minute. I forgot my calculator, but it's okay, I have a phone. So I'm getting 59.6. Well, I'll just write all of them out there. So 2 sig figs would be 60 minutes. Any questions? There's a whole bunch of, all these variations on this question that could be asked. we could give you the time and give you the current and ask you for the mass of the thing, right? Or we could give you the time and the mass and ask you what does the current need to be, right? Change the silver to something else. It might be 2 electrons per mole, or 2 moles of electrons per mole of calcium or something. 60 minutes.